calibrated one of our material models to it, and then saved that calibration so that you can then use it. Now, this is intended to be used as a replacement for what we'd say is call a, quote, generic material model. So a lot of times here when we're running simulations, our customers tell us that that part is made of ABS, or that part is made of PEEK, or that part is made of polypropylene. And they want an answer tomorrow. They are not willing, they either don't have the resources or are not willing to pay for us to do a full test, set of tests on that material to then run our finite element analysis. And we know many other engineers face the same problem. So we typically have to go online and get the spec sheet for that particular material, or sometimes we don't even know and we're just told ABS as a general material. So we have to get material properties for ABS from, say, MatWeb, and then at that point we basically have a modulus and a Poisson's ratio and maybe a yield stress, but we don't even know what happens after that yield stress. So these models would be used in place of that. Again, you have the caveat that it's not your exact material, and that can matter significantly, but you have more information than just an elastic modulus and, say, a yield stress. All the models that we've developed have finite strain capabilities, and they're all rate dependent. We also have the models available for different unit systems that we'll go over in a second. Currently, to use the Veryst Material Database, you have to have a PolyUMod license. It checks out tokens for the PolyUMod license just as you would if you're using a PolyUMod material model. And that depends on your finite element solver, how those tokens are handled. So for the test data, all the material models we have in the Veryst Material Database at this time are calibrated to test data that we collected here at Veryst Engineering. We do not provide the raw test data to the user. We only give you the model predictions. But we do give you a fairly extensive amount of information on the testing that we performed and the model predictions. So if you have PolyUMod and MCalibration installed, you can look at those sheets, and those are in these two locations here. So they're in the case studies folder of your main installation. We also have a user's manual that gives you some more information on what the flags are that you need to use and any settings that you need to use to implement this in Abacus or ANSYS or any of the other packages. So that's the very brief introduction that I'm going to give for just talking. But at this point, I just kind of like to walk you through some different things. So first, I am going to show you an example report that comes with that comes with the Veryst internal database. So this is where you would go as you're determining whether you can use this particular material for your simulation. You come here to find out more information about the material and the testing that we did. So there's a title page. Then the next side page gives a brief outline on the testing that we performed. So for this material, which is a PolyUMod 6.6, we tested all this testing was done at room temperature, so 23 degrees Celsius. And then you can see here the testing that we did. We did monotonic uniaxial testing at 2 strain rates. So these are quasi-static stresses. And then we tell you approximate failure strains. So this material failed between 30% and 70% at these strain rates. We also did monotonic uniaxial compression at this rate with a max strain of 50%. And then we also did cyclic uniaxial compression at these rates. And we put relaxation segments in there as well. So we're getting some relaxation data for the calibrated material model. After you've seen what the model looks like, we show you some predictions. So here are predictions for this model that we've created and calibrated. And so we show 4 uniaxial tension simulations here, and so you can see the behavior. This could be useful for you so you can really understand how the material behaves. This gives you a lot more information than just a spec sheet would, which might tell you the yield stress, which for this material might be up around, is anywhere between 52 to 70 MPa, depending on the rate that you're at. And it would give you the corresponding yield stress, strain, excuse me. And then the next slide just shows you a similar result, but for but for compression. So again, you can see how the material behaves in compression. The next slide shows you how the material behaves cyclically. So you can see here the first cycle, which is about 5% strain. There's not a lot of hysteresis, but there is a lot of plasticity. Then as you get to higher strains, you get more and more hysteresis and increasing plasticity as you go larger and larger. And then just so you would be able to compare to a spec sheet yourself, we have listed here what we call specification sheet values or technical data sheet values. So for the different modes that we had those on the previous slide, we tell you the engineering strain rate and what the modulus was at small strain. In this case, it's 1%, and then the yield stress and the yield strain. One thing to note is those are the yield stress and yield strain according to the 0.2% offset method. So that is different than what you might see according to ASTM D638 or the corresponding ISO standard. And then last, we give you the small strain Poisson's ratio that we use for this model, which was 0.4. That should be it for this one. And again, you can see here that we have another model for ABS. Similar information and all structured in the same way. So once you've seen one of these reports, you should be able to see, quickly understand the remainder of the reports. So those are the reports that we provide. I'm not going to go through the user's manual right now because I'd rather get into the live demonstration. So that's what I'm going to show you now. So right now I'm going to open up MCalibration, just a new MCalibration file, and I'm going to go over here to calibrate. So I don't have anything in here. I don't have any experimental data. So I want to use one of these models, and I want to play with it. So I hit the Set Material Model button down here. I open it up. You can see now at the top, if you're familiar with MCalibration, this library material models used to not be here. It used to just have PolyUMod models right there at the top. So you can see that we have, I believe it's 16, maybe it's 15, material models listed right here. And you can see what they are. So we've got a PTFE, a PET, PA66 that I showed you. There's an ABS. So I'm gonna, so those are some of the material models that you have. We also have some additive manufactured materials here, PA11, some polyurethane, a cyanate ester, and then we also have some models that have, we do have a material here that has 3 different models. So this PEAK has only low rate data. This PEAK material model has both low rate and high rate data. This material model here has temperature dependence built in as well. So we do have one model right now with temperature dependence, and it's something we're considering adding more for. I'm going to go to the ABS material here. And then if you look in the description, it gives you a little bit of information on what you have here. Gives you just a brief introduction, and then tells you what you need to use the material model. And here you can see the 4 unit systems that we currently support in the material database. There's Newton meters seconds Kelvin, millimeters seconds Kelvin, Newton millimeters milliseconds Kelvin, and then there's an English system here as well. Other than that, the next 3 parameters are optional. These are advanced parameters that are available in PolyUMod, as well as the Veryst Material Database. You should start with these as default, and then if you have problems, then we can work through changing those with you. So I'm going to choose this model. You can see here the model is here. The input card is very short, just 2000. It's just these numbers here. Now I'm going to create some virtual load cases here. So let's look at this intention. So I've got 6 rates, and I'll hit run once. I'm going to look at this in engineering stress and engineering strain. Just hide that. So you can see here, this is the stress strain response. But what if I wanted to see, how this material behaved in shear? So I'm going to add a shear test here. I'm going to do it at 0.1 strain and up to maybe 40% strain. I'll change the loading mode here to simple shear. Hit save, and now I'll run that load case. So now you can see how this material behaves in shear compared to how it does in tension. And you could add similar load cases if you're interested in, say, biaxial tension. So say we wanted to change this one to biaxial tension. We'll come here to loading mode, change to biaxial, hit save, and we'll run that selected load case. And you can see it's there. So as we'd expect, it's stiffer, yield's a little higher than the other one. And so you could play around with this as well. We're going to change this back to tension quickly. And we're going to add a stress relaxation segment for, say, 30 seconds. So we run this one again. I'm going to turn all these others off. So you can see here, this is stress versus strain. There's a hold section there, but if we look at stress versus time, we load up, we get significant yielding, and then for the last 30 seconds, you see the stress relaxation. So this is how you could explore how the material model behaves in case you want to see what features or what you might expect when you get to your finite element model. Then you can go through and check these for all the materials we have. So if we then wanted to use it, we could export the model. And I'm going to show you some examples in Abacus. So I could choose here Abacus input file and hit save. I'm not going to do that because I already have the model saved. So I'm going to show you two different material models in the input file for Abacus. So this is the material model for ABS. So you can see here it's very simple. There are just 5 constants you need to give it for the user material. It is invoked as a user material. This is the number of dependent state variables that are needed, and here's the density of this material. And similarly, here's an example for the PolyUMod 6.6. Again, 5 material parameters and the density. Very simple input card. So now if I go over to Abacus CAE, I'm going to show you quickly just the model that I put together. Excuse me. So I've just put together a very simple model here. This is your normal hole in a thin plate simulation here. We're not talking about engineering or finite element analysis if we haven't simulated a hole in a plate. So I figured that would be appropriate. So we just have a mesh throughout here. If I look at my boundary conditions, I have symmetry boundary conditions on this side, and this face. And then I'm just applying a displacement boundary condition along this entire surface. And that's the loading that we have. And I showed you the mesh. And if we go to property here, you can see that we have a bunch of different materials that I've run this for. And so there's this Veryst Database ABS material. And you can see, if you look here, it's just that user material that I showed you earlier. So those details aren't too important for you if you're not familiar with Abacus. But one thing I did want to show is I've run the simulation twice. I've done it once with the Veryst Database ABS model, and then I've also done it with the ABS model that I got from online. This is just an elastic plastic modulus with the Young's modulus and Poisson's ratio shown there, and then the yield stress and plastic strain here. I've made this perfectly plastic because I don't have any other information from online. So to give you an idea, this is what I downloaded earlier from MATLAB. So this is an overview of ABS materials, and you can see here, the ranges here are quite large. So if we talk about modulus of elasticity, they have values from 1 to 2.6 GPA. So that's a huge range. How do you know which value to choose? Elongation at yield is very large. Elongation at break, the yield strength, very large ranges. So I just chose values that kind of match the material that we tested here at Veryst Engineering. So I've shown you my jobs. I'm just going to show you 2 results here. So on the left here, I've run a simulation. That should be the Mises stress, excuse me. So on the left and the right, I've run the same simulation. On the left is the matte web material model. That's the elastic perfectly plastic. And on the right is the Veryst Material Database. And you can see here the stress contours can be very different. The contours I've made here, the legends, are the exact same for the two. But we're seeing significantly higher stress here than we are in this material. And that's because we've done a very different material model. So we're going to get a very different behavior. The other thing that I've set up beforehand is I wanted to show you the results. So say we are running this test as an experiment, and we want to define the force versus displacement of pulling this hole in a plate to whatever displacement I applied. So how do these three material models compare? So I'm going to plot you results from all three, from three different load cases that I ran. Excuse me, I grabbed the wrong one there. There we go. So these are three force versus displacement curves for this hole in the plate that's been run in three different cases. So the green line is what we have from matte web. So you can see here we're linear elastic. We started to get some yielding, and then basically this force drops a little bit, but because that's where we're perfectly plastic. And if I look at the Veryst database, force versus displacement, I've got two curves. There's this brown line. This was run at the same strain rate, the same displacement rate as this green line. So you can see it's much smoother. We're getting a different response post-yield. And then I took that same that same loading, but I increased the speed with which I pulled it by a factor of 10. So I'm going an order of magnitude higher on the strain rate. So you can see here the power of the Veryst Material Database. We get a completely different, or we get a different response. We see stiffer response as we would for these materials. But the elastic perfectly plastic is not going to change. It's going to stay the exact same way. And you could make a change with different model settings, but if you don't have the data from the supplier, you know, there's not really any use to doing that. So this shows one use for it. I also did the same thing for a PolyUMod 6.6. And so I'm going to show you those three plots there. So this one, I just chose a random grade of PolyUMod 6.6 off of MattWeb, and I use their values. That's what gives me this blue line here. And again, it's elastic, perfectly plastic. So it's linear, and then you see rollover as you start to see yield. Whereas the Veryst Material Database looks completely different. The material that we tested, the particular grade of PolyUMod 6.6 had a much lower yield stress. But it also rolls over significantly slower than the MattWeb elastic plastic material model. So these are things you need to keep in mind. You know, we've developed this so that you can get a better estimate of your materials as you get to those larger strains when you need more than just the elastic modulus. But you do have to look at your results very carefully and make sure that you're using the results appropriately. You know, these can give you very good insights into whatever you're trying to simulate, but it might not be the answer. It's something you need to make sure you investigate very thoroughly to make sure you're using the results appropriately. So that is all I have right now for the webinar. That's all I had planned out. But I would be happy to take any questions that you have or suggestions. So before we get to the questions, we are looking for 2 suggestions. We're going to continue these webinars if you continue to find them useful. So if you have any suggestions for the webinars, please let us know. You can send me an email, Jorgen an email, or just send it to our general Veryst contact@veryst.com email, and that'll get to the right person. We're also going to be continuously expanding the material database. So if there are materials that you think really should be in there, let us know. We have a list of our own that we'd like to include. You know, we're going to be working on getting some elastomer type materials in there, a TPU type material, and then broadening the thermoplastics we have. But any materials, any advice you could give us that would help you the most would be very useful. So please send us an email. So that's it. If you have any questions, please feel free to ask them now, or you can reach out later. And thank you very much. Hi, David. Not a problem that you joined late. We will be posting this online on our website, a recording of this on our website afterwards. So we should send a link once that is up and you can see anything you missed. But the database does not contain the experimental data, just the calibrated material model. So it's, yes, just the model, no experimental data. Well, if there aren't any more questions, thank you for coming to our webinar today. Please let us know if you have any suggestions for webinars in the future or for the Veryst Material Database. You can always, excuse me, you can always reach me via email at S as in Sam, TELLER @veryst.com, or here's my email address right here. Please reach out if you have any questions or if you'd just like to talk about a problem you're working on. Thank you very much. Look forward to the next webinar that we do.